This one here is, of course, review from the last couple class periods. It says, which of these elements are expected to have similar chemical properties? Select all of the answers that apply. Correct choices. Unfortunately, B and D don't work. Why do A, C, and E work? What do we look for?
They're in the same column.
Okay, same column, exactly, same group. So remember, if they're in the same group, they have similar chemical properties. And so if they're outside of those groups, you look at magnesium, calcium, and strontium. And if you're looking at your periodic table, which you may as well have out, we are going to be writing on these some more today. So if you need a copy, extra copy of the periodic table, I have some out here. As again, we are going to be writing. Come and grab them now if you need one. We will be writing on them some more today. But again, if we look at these, we have magnesium right here. We have calcium, and then what was the third one? I think we had strontium on here as well. So these three here would have similar chemical properties. Then after this, which of these elements are paramagnetic? Select all of the answers that apply. So if we check these out, correct choices were A, B, and C, which was nitrogen, tungsten, and sulfur. If we go back through and look at the ones that we had at the end of the hour, last class period, we had, well, first of all, we had nitrogen and tungsten, and then we had at the very end of the hour, you were to work on these yourself, they were the sulfur and zinc. We said that in order for something to be paramagnetic, it had to have unpaired electrons. So again, if it's paramagnetic, it had unpaired electrons. So if we look at the nitrogen and tungsten that we did, we see that we have 3 unpaired electrons right here. If we look at the tungsten, we see we have 4 unpaired electrons right here. If we go to the sulfur, we see we have 2 unpaired electrons right here. And then if we go to zinc, which has 0 unpaired electrons, that would tell us that zinc is not paramagnetic, but rather would be diamagnetic, because in this case, all of the electrons are paired up. So again, we look at the pairing of the electrons in those orbitals. Any questions on any of these? Okay, now the one thing we did not get to in our last class period was the concept of ferromagnetism. And if we talk about something that is ferromagnetic, ferromagnetic is different than paramagnetic and diamagnetic. And this here is a special type of magnetism where the spins of the unpaired electrons are aligned. So ferromagnetism is a special type of magnetism where the spins of unpaired electrons are aligned. And which element do you suppose can exhibit ferromagnetism? Ferro would refer to which element?
Iron.
Iron, exactly. Iron is, ferrum is the Latin name for iron, and you can cause iron. I don't know if, I mean, this used to be things that we would do before the days of the internet and everything. We would make our own magnets and everything, and you can make your own magnet. Very simple. I don't know if any of you have ever done it before, but you can take an iron bar and you point it north and south. You can take a hammer on it and hammer it really hard, and when you hammer it really hard, you can go ahead and knock the, this is true, you can knock the electrons into alignment, and then if that iron bar remains suspended, then the magnetic, iron bar will align it with the magnetic north and south poles, just automatically. So ferromagnetism is not a very common type, but of course we do know that there are such things as permanent magnets, which we do induce magnetism in those devices. So any questions with these? All right, then our last question on the Socrative app today is one that has you refer to this table, and let me pull this table up here. Here we go. So take a look at this periodic table. Now this is a table of actual electron configuration. This is found on page 362 of your text. Look these over and find one element that has an electron configuration that is different than what we would predict by the building up principle. Find one and make sure that yours is different than a neighbor's. That means if you don't recognize it, talk to a neighbor here to figure out what the patterns are and where they might lie. There are several examples up here. Find one. Several of you aren't talking, so those that aren't talking, find someone to talk to, someone that figures out where they're at, so you know where to look. Let's do it. I know it's shortly after 8 in the morning, but we can talk in the mornings. There's only 8 of you that have locked in an answer, so let's see if you can figure them out. Okay, let's get some answers locked in here, please. Okay, we got 11 of you. Let's have some more. Helium isn't one of them, by the way, whoever put helium in. Okay, that is one that is on target. So, if we check out these answers, platinum, let's see if platinum is one of them. We'll come back to platinum here. Platinum is right here. That is one of them. That is correct. Let's check out another one. Chromium. Let's see if chromium is one. Yes, chromium is one of them. Let's find PD, palladium. Yes, that is one of them. I see iron. Iron is not one of them. Hydrogen is not. Aluminum is not. Cadmium is not. So why are these 3 here, of the ones that people answered, why are these 3 ones that are exceptions to the building up principle? What makes them exceptions? I zoom it in a bit. What would we predict the configuration of chromium to end with? D4, exactly. If we look at chromium, we see its configuration is shown as ending with D5. For palladium and platinum, what would we expect these configurations to end with here? D8, right. And we see that palladium ends with a D10, platinum with a D9. So as you look at these here, we have D1, D2, D3, D4, D5, D6, D7, D8, D9, and D10. So in saying that, what is another one here that seems to not match up with the prediction? Molybdenum. There we go. There's another one. Where else?
AG and AU.
AG and AU. Exactly. So now if we locate where these are at in the periodic table, where they're at in the periodic table, notice that there seems to be a whole bunch of them here that end with a configuration of D10. We have a tendency here towards a configuration of D5. And so what's significant about this is that if we go back to where we were looking at the other day when we were looking at these orbital diagrams, if we have a D5 or a D10, a D5 or a D10 represents either entirely filled d orbitals or d subshells or half-filled orbitals. And by half-filled, we're saying that the entire thing. So there's a tendency towards a D5 or a D10. Now, the explanation behind that, physicists, physicists and chemists don't exactly have an explanation as to why that is, other than it is likely that they are more stable in these configurations, that either the entirely filled subshell is stable or a half-filled subshell is stable. And that is, when we say stable, we're pointing to something that would have a lower potential energy, that the atom itself has a lower potential energy when you have these d subshells that are either entirely filled or half filled. And had we gone down and looked at the F's, so let's come back here to the F's, which we didn't see before, we would see that there's a whole bunch of these here that wind up with this F14s. So we see the F14s show up a whole lot, and then we probably see the F7s show up quite a bit as well here. So an F7, 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 F7. And so there's something then that must be stable or lower in potential energy for the entirely filled subshells for the D's or F's, or the half-filled arrangement. But beside that, we don't really know for sure what the reason for that is. And so if you ask then, do we need to know the actual configurations for the elements, or how do we know them? Well, if you think back to where we started all of this, we started by looking at the line spectra for the elements. And so when we look at the line spectra for all of the elements, it turns out that these configurations are determined based on calculations associated with the line spectra. And the line spectra points to these configurations rather than the ones that we predict through the building up principle. So again, these come from observations of the line spectra. What else should we know about these? Well, if I were to ask you which elements have exceptions to the building up principle, so this one here, let's just ask it. Let's not look at the periodic table, or let's not look at this one, but let's instead just look at your periodic table. And I'll load this one up here and ask you this question here. Without looking at the periodic table that shows the actual configurations, which elements might one expect to have an electron configuration that is different than the one predicted by the building up principle? So you can look at your periodic table, but again, without looking at the one that we just had up here, where might we expect to find some exceptions? We'll give you about 15 seconds to get answers locked in. And then we'll count down on these. 5, 4, 3, 2, 1. And if we check them out, again, we'd expect to find them around copper and molybdenum, not for aluminum and tin, if you were one of them that put aluminum and tin into there, because if we look at where aluminum's located, aluminum's over here, it's in the P block, tin is down here, also in the P block. We found exceptions. Where did we find those exceptions to be? In the F and the D block, and specifically, it's not just anywhere in the F and D block. We typically find them towards the end of the D block, not at the very end because we expect them to end with D10, so toward the end of the D block, and also towards the middle of the D block. Not in the very middle because we'd expect to find the D5 here, but again, like right before the halfway point, we have that tendency towards the half-filled and the entirely filled subshells. So any questions on those? All right. Now, the next thing we're going to get into here, and just take you back to some reminders here. First of all, reminder that the last day to withdraw is next Wednesday, the 27th. If you're concerned about your status in this class, please see me. Also a reminder that we do have an ACS Final Exam Study Guide that is available at the reference desk in the library. That Final Exam Study Guide does cover the entire year. So unfortunately there's not one specific to the first semester, but if you were to go through that, you can find some examples of questions that you can study. Just look to ones that appear as if they are from the first half of the semester. And hope you can't figure out which ones as the first semester topic of things we covered, then you probably ought to be studying there in the first place. Okay, so where we're headed next here today is something that we call periodic trends. Periodic trends. And so it turns out that there's a number of things where there are trends in the periodic table. So by looking at the periodic table and using only the periodic table as a resource, we should be able to determine things that are happening to things such as the ionic radius. That's ionic radius is one of them. I have the atomic radius up here. That's another one. We are going to be talking about ionization energies. And so not only should we be able to identify what the trends are, but we should be able to explain why the trends are the way they are. And so the first one we're going to talk about here today is the atomic radii. And so the atomic radii, we talk about radii, of course, radii is the plural of radius. And so these here measure the radius of atoms as they correspond to different elements. And so the first thing we're going to do before we explain the reason why is to have you look at this and then see if you can identify the trends in the atomic radius. And remember that the radius is the distance from the nucleus, that is the center, to the outside of the atom. So it's not the diameter, but is the distance from the nucleus to the outside of the atom. So take a look at this data. And I have it presented here another way, so you can look at this table of this graph, or I also have this in table form, like this right here. What are the trends in the radii within the periodic table? So we'll look at this. Look at this right here. I see that my second one gave it away, so we'll just look at this first one. So I'll give you about 15 seconds to get an answer locked in. So we're going to count down on this one. 5, 4, 3, 2, 1. And these are the trends. First of all, A, they tend to increase as we go down within a group. And secondly, they tend to decrease as we go across the period from left to right. So again, coming back to here, we see that as we go down within a group. So if we're picking out the lithium, sodium, potassium, rubidium, and cesium, the radii tend to increase as we go down. So if we're looking at our periodic table now, and we want to add in some trends here, we can add in some trends for the atomic radii. And as we add in the trends for the atomic radii, again, as we go down within a group, we see that the values are going to increase. Values will increase as we go down within a group. And again, that comes from the fact that if we look at lithium, sodium, potassium, rubidium, etc., the radii here become larger and larger. Then if we look within the group, we're going from lithium all the way across to neon. We're going from sodium to argon, potassium down to krypton. We see that here within a period that the values tend to decrease. So again, as we go across from left to right, we see that the values decrease. Now this might be a bit counterintuitive. That is something that we don't quite predict. In fact, if we were to look at these two trends right here, the increasing as we go down within a group and the decreasing as we go across from left to right, which one of these two would we predict without having much knowledge about chemistry? Which one of these two makes the most sense? Right, the increase should be one that makes sense, because what happens as we go down within a group? More electrons, right? So with more electrons, we should expect to see a larger radii. It should make sense. But it's not just there's more electrons. If we want to truly explain what it is, remember that the value of n here is increasing. Remember that the value of n stands for the energy level. And so we talked about the energy levels, we talked about them being increasing distances from the nucleus. So it would make sense that as we add in more energy levels going down, that we'd expect the radius to increase. Okay, but the one that probably doesn't make sense is as we go across from left to right, that the values decrease. Because after all, even as we're going across from left to right, especially if we look at period 2, we're going from 3 electrons in the atom all the way up to 10 electrons. And so we think by adding in more and more and more electrons that the radius should be increasing, when in fact it is decreasing. Now the way that we explain that is through something called the shielding effect and the effective nuclear charge. And this is described, and we have a figure on page 368 in your text. But again, it's something that's referred to as the shielding effect and the effective nuclear charge. And the effective nuclear charge we define like this. So again, the effective nuclear charge. The effective nuclear charge is the nuclear charge that is experienced by valence electrons. So again, the effective nuclear charge is the nuclear charge that is experienced by valence electrons. And so if we were to look at an example, let's say we look at something like lithium. And what we're going to look at here now is what is the effective nuclear charge. We are going to write out, even though the Bohr model is not entirely accurate, it still is an effective way to examine the effective nuclear charge. And so if we were to look at lithium and write out its electron configuration, the electron configuration for lithium would be written as 1s2, 2s1. And if we then want to show the arrangement of those electrons, first of all, we go to the nucleus and we talk about the number of protons in the nucleus of lithium. And so if we want to talk about the number of protons in an atom of lithium, lithium right here would have how many protons in its nucleus? It would be 3, because the atomic number of lithium is 3, and so we'd say it has 3 protons. Then it has 2 different energy shells. It has the first energy shell where n is equal to 1, and the second energy shell where n is equal to 2. In the first energy shell, we would simply have 2 electrons, or the first energy shell would have 2 electrons, and in the second energy shell, we just have 1 electron. So the way that we would calculate the effective nuclear charge is like this. We would take the nuclear charge, and the nuclear charge is simply what is the charge in the nucleus, which in this case is 3 positive, and then we'd subtract out the number of electrons that are said to be shielding the valence electrons from that nucleus. So again, this shell right here, the first energy level right here, this is shielding the valence electrons from the nucleus. In other words, this valence electron right here has to see through this shield to see the nucleus. So in effect, what's happening is that this nuclear charge of 3 positive is being shielded by 2 negative charges, and as a result, we'd say that the effective nuclear charge that that valence electron sees is a single positive. So again, it's the 3 positive charge of the nucleus minus the 2 valence electrons. If we went on to something like nitrogen, nitrogen has the electron configuration of 1s2, 2s2, 2p3. If we were to draw out a structure of nitrogen in the nucleus, nitrogen would have how many valence nucleus? The nucleus here would have how many protons? In the case of nitrogen, it would have 7, because its atomic number is 7. Okay, then if we were to fill in the electrons, there's 2 energy levels here for the nitrogen. There's the first energy level. The first energy level has how many electrons in it? Just 2. And the second energy level has how many electrons in it? More than 2. How many are in the second energy level?
5.
There's 5. So we put in 1, 2, 3, 4, 5. Okay, so now, if we want to calculate what's called the effective nuclear charge, again, the effective nuclear charge is the nuclear charge experienced by a valence electron. So if we pick out, it doesn't matter which valence electron we pick here. If we pick just one valence electron, let's pick this one right here. If it's looking into the nucleus, this valence electron is being blocked by how many inner level electrons? Simply being blocked by 2 of them. And so if this is being blocked by 2 of them, what is the effective charge that that valence electron is experiencing? It's going to be 5 positive. This is simple math, folks, because the nucleus is a 7 positive. It's being blocked by 2 electrons. So then we take 7 minus 2, and it's seeing a total effective nuclear charge of 5 positive. Let's see how you're understanding this. Let's go to neon. I'm not going to do this one for you. So for neon, let's see what you can calculate. What is the effective nuclear charge experienced by valence electrons in an atom of neon, which again has an atomic number of 10? What is the approximate effective nuclear charge? If you're not sure how to do it, talk with a neighbor. How are they doing it? And we'll give you about 30 more seconds. Let's get our answers locked in. We'll count down. 5, 4, 3, 2, 1. And we see that we have the 8 positive. So if I were to draw this out really quick, our electron configuration is 1s2, 2s2, 2p6. The nucleus has a charge of 10 positive. Inner level would have 2 electrons. The outer level would have 8. So 1, 2, 3, 4, 5, 6, 7, 8. An outer level electron right here is going to be looking through to the nucleus, being blocked by 2 electrons. And so those are considered to be inner level electrons. And those inner level electrons go by a couple of different names. We also refer to them as being core electrons. We also refer to them as shielding electrons. So they go by a few different names, and basically what they do is they shield the valence electrons from the full experience of the nuclear charge. And actually when I talk about these effective nuclear charges, I'm saying that they're equal to this. That's actually not correct. If you take a more advanced physical chemistry class, you are going to calculate more specifically what they are. This squiggly line here doesn't mean that they're equal to, it means that they are approximately equal to those values. There's actually a more precise way to calculate them because those other electrons do have some effect. But now what that means is that as we go across the periodic table, if we come back to the periodic table here and we just looked at lithium, nitrogen, and neon. So as we go across from left to right, what is happening to the value of that effective nuclear charge? The nuclear charge is increasing. And if we remember what opposite charges do, opposites will attract each other. If opposites attract, that means as we go across from left to right, that is going to attract that valence shell in closer to the nucleus, and as a result then, we're going to see as we go across from left to right that the nuclei actually, not the nuclei, the radii actually decrease in size. So again, we explain the decrease in radius as we go across from left to right by using the effective nuclear charge. If we looked at one other example, we went out a little further. Let's look at something like arsenic. Arsenic. If we want to look at its effective nuclear charge, we write out the complete electron configuration for arsenic. So arsenic is right here. We know its configuration is going to end with P3, specifically 4P3. So out here we'll have a 4P3. Working backwards, we'd have a 4S2, then a 3D10. Well, actually it would do a 3D10 and then a 4S2, and then let's see, there's going to be a 3P6, 3S2, 2P6, 2S2, and then a 1S2. So now if we did this try doing this now without writing out the entire configuration like I did, or without writing out the entire boron model diagram. But let's see if you can figure out what the you should be able to do this now without drawing out the picture. See if you can guess what the effective nuclear charge is that would be experienced by valence electrons in arsenic. Remembering again that the shielding electrons are all of the inner level, or all of the core electrons. Not just the first energy level, but it's all of the core electrons. So if you need to look at the configuration again, here we are. We'll give you about 15 seconds to lock in an answer, and you should almost be able to eyeball it right away. And we're going to get our answers locked in here, please. We're going to count down 5, 4, 3, 2, 1. Before we give that answer, how many valence electrons does this one have? I hear 3, I hear 5. How many is it? Well, valence shell. What is the outer energy level here? It's the 4th. So we have these 3 here, and what else? We've got these 2 here, so these are all a part of the 4th energy level. So altogether, arsenic has how many valence electrons? 5 valence electrons. And so we get that 5. If you're not sure how to get that, how many electrons does arsenic start with altogether? 33. How many inner level electrons are there? 28. Exactly. So we have these 5 right here that are from the valence shell. And again, we get the valence shell based on the fact that we have those that 4th energy level, and they're showing the 5 electrons in it. So if we're looking at it, you'll recall that there's going to be 33 protons in this nucleus. There's going to be several, like 3 different levels in here. If we look at 3 different levels, there's going to be 2 of them in this level. In the 2nd energy level, there's going to be 8. Then the 3rd energy level, there's going to be 18 electrons. Then sitting out here, we're going to have 1, 2, 3, 4, 5. So basically, if you know the number of valence electrons, that number of valence electrons is going to wind up telling us exactly what that effective nuclear charge is, or it should be a value of 5 positive. Because again, there are going to be a total of 28 inner level electrons. All of these are inner level electrons, 28 of them altogether will be blocking the valence electrons from the nucleus. But again, if we were to go back and look at the periodic table, we would see that the general trend as we go across from left to right is that the radii decrease, and we should get that then by looking at this value going from sodium on across, potassium on across, and we see this general trend in the radii going from left to right. And it's simply because the effective nuclear charge increases as we go across the period from left to right. Any questions on that? Dibley?
On this test, will we have to write out the whole configuration, or can we just shorthand it to get the answer?
If you can shorthand it, that will generally be just fine. Anybody else? Okay, next up, let's go ahead and look at this graph. This graph here now is with respect to what we call ionization energies. And let's define what an ionization energy is. We define the ionization energy as being the energy required to remove an electron from an atom in the gaseous state. It's the energy required to remove an atom or an electron from an atom in the gaseous state. Now what we're going to see is that they're given some different labels. We're going to hear referral to the first ionization energy. We will see referrals to the second ionization energy, which we label as IE sub 2. IE sub 3 would be the third ionization energy, fourth ionization energy, fifth ionization energy, and so forth. So when we see the first ionization energy, like we have right here, this is the energy required to remove one electron. Again, the second ionization energy would be the energy required to remove the second electron from an atom. The third ionization energy would be the energy required to remove the third electron from an atom, and so forth. So this here is a table of the first ionization energies. And so I'm going to have you look at this table now. We're going to develop trends again. And upon looking at this table, let's see what you can tell what the general trends are for the first ionization energy within the periodic table. And select all of the trends that apply. Again, obviously there are some exceptions, but as a general rule, what is the trend in ionization energies? So you should have one trend for the group, one trend for a period. And we'll see how we're doing here. We'll get our answers locked in then, and we'll count down. 5, 4, 3, 2, 1. And the trends, very good. They tend to decrease as we go down within a group, and then they tend to increase as we go across a period from left to right. So again, coming back here, within a group, we see that as we go within a group, the values tend to decrease. And if we look within a period, we see that as we go across from lithium to neon, that the values tend to increase. From potassium to krypton, that tend to increase as we go across from left to right. So again, if we're looking at our periodic table and we're putting in these trends, we can label one here for the ionization energies. And specifically, this is the first ionization energy. The trends are that as we go down within a group, the values will decrease. And as we go across a period from left to right, we see that the values are going to increase. And there's one important feature to notice. How do these trends compare for the first ionization energy? How do these trends compare to the trends for the atomic radii? The trends are exactly the opposite. As the atomic radii increase, the first ionization energy will decrease. And as the atomic radii decrease, the first ionization energies tend to increase. Now, it's not exactly an inverse proportion, but it certainly is a general trend, an inverse trend. Okay, that's not a proportionate trend, but certainly they do just the opposite. And the explanation that we give for the first ionization energies simply has to do with the atomic radii. Remember that as we go across from left to right, what's happening to the effective nuclear charge? So they go across from left to right, the effective nuclear charge is increasing. And the electrons, though, going across from left to right, these valence electrons are all in the same shell. So if that effective nuclear charge is increasing, remember that opposites will attract, and if they attract, that's going to make it more difficult to remove an electron. So again, the greater the effective nuclear charge, the more difficult it is to remove those valence electrons. And then as we go down within a group, we didn't calculate this at the time, but if we had to approximate the effective nuclear charge going down within the group, what is the approximate effective nuclear charge for all of these here in group 1A? They all have one valence electron. So if they all have one valence electron, the approximate effective nuclear charge in all of these is going to be about 1 positive. Because again, with one valence electron, all the rest of the electrons are going to be inner level or core electrons. And so if these are all 1 positive, these are all experiencing the same effective nuclear charge. The difference is that these are further and further away from the nucleus. So even though they're experiencing the effective nuclear charge of 1 positive, and again it's approximate value, because they are further away from the nucleus, it's just like if you had two magnets attracting each other. The most difficult portion of pulling two magnets attracting each other away from each other is when they are actually in contact with each other. If we start with them further apart, they're going to be easier to move apart. So again, it's simply easier to remove an electron from an atom the further away it is from the nucleus. And so we can pretty much describe them based on the effective nuclear charge, or we can compare the first ionization energy to the atomic radii. So as long as you understand what effective nuclear charge is, you should be able to explain what's happening here with the first ionization energies. Any questions on the first ionization energies? Okay, if we go down to, let's see, how do these trends compare? Blah, blah, blah. I asked you these successive ionization energies. Okay, so here's what happens when we look at successive ionization energies. You remember that the first ionization energy is the energy required to remove the first electron. The second ionization energy is the energy required to remove the second electron from an atom. The third ionization energy is the energy required to move the third electron. Now these are showing the successive, these are called successive ionization energies for the elements sodium and magnesium. If we look to sodium, where is the biggest jump between which successive values?
First and second.
First and second. If we look at magnesium, the biggest jump is between second and third. Well, if we go back to sodium, sodium has how many valence electrons? Just has 1. Magnesium has 2 valence electrons. So these first ionization energies, in this case the first and second for magnesium, these are low because these are the electrons that are the valence electrons. And so it's real easy to remove those valence electrons. But in the case of sodium, as soon as we remove that valence electron, then all of a sudden, all we have left for sodium, if we write out that configuration for Na, we have 1s2, 2s2, 2p6, and 3s1. If we get rid of that one valence electron, we are now down to a total of 10 electrons altogether. But now these 10 electrons, 8 of those are now the new valence electrons, so to speak. And these are going to be a lot closer to the nucleus than this one valence here. And that one valence electron then is going to be more difficult to remove because it is now much closer to the nucleus. And if we went on to something like magnesium, magnesium starts out with the electron configuration that looks something like this. If we remove one electron and goes down to 3s1, this one electron here is still a valence electron. It's going to require more energy to remove that second electron than the first one. But if we now go down to removing this one here and go to that third ionization energy, it's going to require a lot more energy to remove that third electron than it would be for either of the first two. So if you were to wind up looking at a table of something like the successive ionization energies for the rest of them, again, you're going to see a big jump when we go from the valence electrons to the core. And again, that's always going to be the biggest jump when we go from those valence electrons out there to the core. Any questions on those trends? Okay, then the last one we're going to look at here today is the electron affinities. And we define the electron affinities like this. At least this is the last of the trends. For neutral atoms, we'll look at some for the ions here in just a moment. But it's electron affinity, and we define the electron affinity as being the energy change associated with the addition of an electron to an atom in the gaseous phase. Now, if we try to look for trends in electron affinities like we did for the ionization energies and the radii, we don't quite see such a nice trend as the other ones. What we should notice is that these groups right here have the values that are most exothermic. Again, these are given in units of kilojoules per mole. And what that is basically telling us is that these elements, the ones in group 7A and 6A in the periodic table, tells us that these have a high affinity for electrons. Now, if you don't know what affinity means, affinity is similar to an attraction or a liking of each other. So they have a high affinity or high attraction for each other. And so the more negative this value is, the more basically it wants to take on an electron. And that should make sense because, again, we know that these are the nonmetals, and the nonmetals are going to be ones that in reactions are ones that tend to pick up electrons quite easily. Okay, any questions you have on those? Okay, then we look at, let's look at ions now. We just finished looking at atoms, let's look at ions. And specifically, let's look at these two ions right here. We're going to look at the sodium ion, and we are going to look at the oxide ion. Let's write out the electron configuration for these ions. Let's write out the electron configuration for the ions. Now, if you're going to write out the electron configuration for the ions, you can first start, if you're unsure of how to do it, start with writing out the electron configurations for the atoms. And we are going to write out the full configurations this time to help illustrate a point. So in the case of sodium, sodium right here has a total of 11 electrons altogether. And so we'll start the 1s2. After the 1s subshell is filled, we go on to the 2s. After 2s is going to be 2p, which holds up to 6. And after 2p, we then go on to the 3s. And again, just as we would have predicted before, everything in this group is going to end with an S1 configuration. Sodium is in the third period, so its configuration should end with 3s1. If we do it for oxygen, oxygen here has an atomic number of 8. Its configuration, of course, is going to end with P4, specifically 2P4. So we go 2P4. For the 2P, we would have 2S2, and before the 2S, we'd have 1S2. And so these are the configurations for the neutral sodium and oxygen atoms. But again, our goal is not to write them for the atoms, but rather to write them for the ions. So now if we write them for the ions, let's look at what that would imply. What does it mean if we write a single positive charge? What has happened to the electrons?
Lost an electron.
Lost an electron. So which electron is going to go away?
3s1.
3s1 is going to go away. And what that leaves us for the configuration is 1s2, 2s2, 2p6. Then if we look at the oxide ion, its charge here is 2 negative. With a charge of 2 negative, what does the 2 negative mean? Means it is gained. How many? 2. So where do they go on to? They go into the P. So instead of 4 electrons in the P, we'd have 6 electrons in the P, which means that its configuration is 1s2, 2s2, 2p6. Now if you were to compare these two configurations, how do these two configurations compare?
The same.
They are the same, exactly. And so if they're the same, we refer to these as being isoelectronic. And we say that these are two isoelectronic species. And the prefix iso means equal. So if you have an isosceles triangle, for example, an isosceles triangle is a triangle that has two sides of equal length. Okay, so isoelectronic means that they have same electrons. These species have the same. So what I'd like for you to do now is to think about this. Don't rush to answer. You are going to answer, but don't rush to answer it. Think about it before putting in your answer. First of all, what is the approximate effective nuclear charge that would be experienced now by valence electrons in a sodium ion? Not a sodium atom, but a sodium ion. And if you need to, write out your picture. Draw out your picture if you need to. So remember, when we draw out our picture, we're showing the number of protons in the nucleus. Then we're showing inner level electrons and outer level electrons. And if you already have that one, the next question is going to be on the oxide ion. You're going to calculate the approximate effective nuclear charge on the oxide ion. So again, if you need to draw out the picture, however it would be, write out your picture. Okay, and we'll give you about 15 more seconds to get this one locked in. And we're going to count down on this one. 5, 4, 3, 2, 1. Correct answer here is 9 plus. Let's see how we get the 9 plus. In a sodium ion, how many protons are there going to be in the nucleus? And where do we get the 11 from? Atomic number, right. The atomic number of sodium here is 11. So these 11 protons. In this first energy level, how many core electrons are there? There are 2. In the second energy level, how many valence electrons are there now at this point? There's going to be 8. So we put in 1, 2, 3, 4, 5, 6, 7, 8. So if we pick out one of these valence electrons here, this valence electron, when it's looking through to the nucleus, is being blocked by how many valence or how many interlevel electrons? It's being blocked by 2. So we would then find that effective nuclear charge by taking 11 minus 2, which is going to give us an approximate effective nuclear charge of 9 plus. So again, these are approximate values. 9 plus is where we're at. Go ahead and try this out now for the oxide ion. What is the approximate effective nuclear charge for the valence electrons in an oxide ion? Take 15 seconds. Get this locked in, please. And we are going to count down on this. 5, 4, 3, 2, 1. And the correct answer on this one would be 6 plus. Good. So if this one is 6 plus, again, we would get this one because the nucleus, in this case, would have a charge of how much? 8 plus. There's 8 protons. Interlevel electrons, there would be 2. And how many valence electrons would there be? Okay, so with 8 valence electrons, there's 5, 6, 7, 8. One of these valence electrons right here is looking through to the nucleus, and it's being blocked by 2 interlevel electrons. So we take that charge of 8 minus 2, and you're going to wind up with an effective nuclear charge then of about 6 plus. Now, we look at this because what this will help you do now is to make a conclusion as to what does this mean about the radius. If we now wanted to compare the size of a sodium ion, looking at what you just drew, reason this out. What should this imply about the size of the sodium ion and the oxide ion? Which one would we expect to be the largest? Reason it out. And we'll get our answers locked in here, please. And we'll count down. 5, 4, 3, 2, 1. Largest is going to be the oxide ion. Ooh, oxide ion. Now, come back to these here and tell why would we expect the oxide ion to be the largest? How many just guessed on this one? Anyone? Okay, just guessed? All right. I'll give you 1 minute, and I expect you to talk this time. Come back and explain which one of these, why would the oxide expected to be the largest? 1 minute. Sounds like you have it all figured out. All right? Well, all figured out. Why does this one have the largest? Looks like you got it, Doug. You got it?
I think like this one has like 6 plus, so it has like less positive charge.
Yep.
So the other one like attracts more of the electrons.
Exactly. Remember, opposites will attract. If we have 9 positive charges attracting the same number of electrons, 9 positives are going to attract them in much closer to the nucleus than 6 positives will. All right? So again, 9 positives attracting the same number. Remember, they both have 10 valence electrons. They have 2 inner level electrons, 8 outer level electrons. The only difference is the effective nuclear charge. So this one has a greater effective nuclear charge that's going to pull that cloud in closer than it will be for the oxide ion. So now, if we went and looked at the diagram, this shows on page 374. This compares the size of the radii of atoms to their cations. So this is showing cations. Remember that cations are positively charged ions. On the left-hand side of each one of these is showing the size of the neutral atom. On the right side, you're showing the size of their respective cation. And notice in every case the cation is much smaller because, of course, if we're losing electrons, not only are we losing a shell, but then we're also increasing the effective nuclear charge, which is going to have the effect of shrinking them out even more. If we come back to these over here, notice that what happens when we add in electrons, the size from the neutral to the anion is much larger. And so we have to remember, we've been talking about attractions, which occur between opposite charges, but we also have repulsions, which occur between like charges. And so if we're adding in more electrons over here, the more electrons we have, then we have more repulsions taking place. So with more repulsions, that's going to serve to increase the size of these ions out here as well. Now, all by itself here, this doesn't really mean a whole lot, but what we're going to see once we get into chapters 11 and 12, we'll start talking about how atoms bond together and how they form crystals and everything, and then atomic size and ionic size ultimately winds up dictating the sizes that we find. And it looks like I'm running a little short of time here, so I got one more thing I want to fit in today, and I think we're just about caught up with where I would like to be. And that is what happens if we look at the electron configurations of the transition elements. So I'm going to put in one more periodic table, and if you need to grab another periodic table, I have some more up here. So I'm going to insert one more periodic table to write on. Here we go. So let's look at something like tin and write out its configuration. And we can write out the shorthand configuration for tin, which we see is right here. If we write out the shorthand configuration for tin, we know that the configuration for tin is going to end with P2, specifically 5P2. And then if we work backwards from here, tin is also going to have all of these electrons, which would take us up through 4D10. And then it would include all of these electrons here, which would be part of the 5s subshell. So it's 5s2. I think I have breakfast on my screen here. I can't write correctly. 5s2. There we. Yeah, something's on my screen. And then before that is going to be krypton. Now, if we were to rewrite this, one of the ways we could rewrite it is as krypton, and then we'd put it in order of increasing values of n, so it could be rewritten as 4d10, 5s2, 5p2. If we want to write out the electron configurations of the ions, there's a couple different ions of tin that form. They are tin 2 and tin 4. So we write out these configurations. The configuration of tin 2 would be the removal of the 2 highest energy electrons. So which electrons do you suppose get removed of here going from tin to the tin 2 ion? The P2s are the ones removed, exactly. So we go from here to put down a 5s2 for D10 as this configuration. If we want to look at the tin 4 ion, of course this means that we're removing a total of 4 electrons. So the 4 that disappear here are going to be all of those here in the 5th energy level. And so the electron configuration for the tin 4 ion would be krypton and then followed by 5s2, not 5s2. What would it be? 4d10, right? Now if we did something like zinc, let's say we look at the zinc 2 ion. If we wanted to write out its configuration, we'd first start out by writing out the complete configuration of zinc. So zinc sits right here with a configuration that ends with D10. Specifically, it's going to end with a 3d10. Remember, if it's in the D block, we take n minus 1d. And then it's going to have, in addition, these over here, which are the 4s2 electrons. And then we put in the noble gas core. The noble gas core for zinc is going to be argon. Okay, so this is the configuration for neutral zinc. If you wanted the configuration for zinc ions then, which is 2 positive, that means we are going to remove which electrons? We remove the 4s2, exactly. We get rid of those. We wind up with a configuration of argon followed by 3d10. Let's see if you can figure out these two, and this is how we will end the day today. Figure out the electron configurations for the tin, not tin 2, the iron 2 ion and the iron 3 ion. Iron 2 and iron 3. Remembering that the electrons that go away first are the valence electrons. Valence are the ones that are in the outer energy level. And then we borrow from the D if we go from there. Looks like we're running out of time here, so let's do these two quickly. We have the iron 2 ion. So with our iron 2 ion, get our answers locked in. This one here would have a great configuration of the D6. And then if we do iron 3, get this one locked in, we'll count down 5, 4, 3, 2, 1. Fabulous. I like when we end with 200%. That's it here for today, everyone. If you didn't get these, here's your iron 3, here's your iron 2.